next periodic trend is ionization energy or ionization enthalpy we call. What is mean by this ionization energy or enthalpy? Ionization, the definition of this ionization enthalpy is the energy required to remove outermost electron. The energy required to remove the outermost electron is called what? Ionization energy or ionization enthalpy. See here, consider an atom. That atom contains protons and electrons revolving around the nucleus. Now, if you want to remove the electron which is present at the valence shell, then the amount of energy required to remove that outermost electron, that is the electron present in the valence shell, that amount of energy, that much amount of energy is called as what? Ionization energy. This ionization energy, how it varies in the periodic table? Important. The ionization energy increases. The ionization energy increases as you move across the period. Across the period means left to right. As you move left to right in the periodic table, the ionization energy goes on increasing. Why it increases from left to right in the periodic table? See here, we know that the atomic radii goes on decreases as you move left to right in the periodic table. If the atomic radii decreases, then the distance between this proton and the electron which is present at the valence shell goes on decreases. The attraction between the nucleus, that is proton, and the electron which is present at the valence shell decreases as the size decreases. Here, the attraction is more between this proton and the electron. See here, the attraction is comparatively less in this diagram, that is in the first group. Here, very difficult to separate this proton and electron. Therefore, huge amount of energy is required to separate these two, proton and electron, because the attraction is more. And here, the attraction is less. Comparatively, if you compare this diagram and this diagram, here the distance between this proton and the electron present at the valence shell is less. Therefore, less amount of energy is required to remove this outermost electron. Therefore, the ionization energy increases as you move left to right in the periodic table. The reason is the atomic radii decreases as you move left to right in the periodic table. That is, the atomic radii decreases, atomic radii decreases, ionization energy increases as you move left to right in the periodic table. The reason, and if you move top to bottom in the periodic table, the atomic radii goes on increases. From top to bottom in the periodic table, the atomic radii goes on increases, which means that the attraction between this proton and the electron present at the valence shell is also what? Decreases. The attraction between this proton and electron decreases because the size goes on increases. As the attraction between this proton and the electron decreases, then ionization energy, that is the energy required to remove this outermost electron, is low. Therefore, the ionization energy decreases from top to bottom in the periodic table. Ionization energy, how it varies in the periodic table. Clear, students? See here how it varies in the periodic table. Ionization energy increases as you move left to right. As you move left to right in the periodic table. Left to right or across you call. Across. And ionization energy decreases as you move top to bottom or down the group you call. Both are there. Clear? Ionization energy means the energy required to remove the outermost electron is called as ionization energy. From top to bottom or from top down the group, ionization energy goes on decreases because the size goes on increases. Left to right in the periodic table, that is across the period, ionization energy goes on increases because the attraction between the proton and the valence shell electron is increases, which means that the size decreases, ionization energy increases. Clear? The ionization energy increases from left to right in the periodic table and it decreases from top to bottom in the periodic table. See here, for example, boron and carbon. Boron is having, if you calculate the ionization energy, you must know how to write the electronic configuration. See here, boron is having the atomic number 5 and carbon is having the atomic number 6. And here, atomic electronic configuration of boron is 1s2, 2s2, 2p1. And here, carbon, it is having the atomic number 6, which means that 1s2, 2s2, 2p2. The size between carbon and boron and carbon, the size of boron and carbon, which is high and which is low, which is small size and which is large size. Here, left to right in the periodic table, the size is goes on decreases, which means that carbon is smaller than boron. Therefore, here ionization energy is more and here the ionization energy is less. Therefore, here if you want to remove this electron, the electron present in the p shell, it is high because the size is small. Carbon is having small size, therefore ionization energy is more, and boron is having large size, therefore ionization energy is low. Here ionization energy is high because the carbon, between carbon and boron, the carbon is having small size because from left to right in the periodic table the size is goes on decreases from top here, and here boron, it is having large size, therefore the ionization energy is less. The other thing to remember here is, see here, if you want to remove the electrons in the nitrogen and oxygen, we will take an example. Nitrogen, it is having atomic number 7 and oxygen is having atomic number 8. While discussing electronic configuration, I clearly mentioned that the half-filled orbitals are stable and completely filled orbitals are very stable. Half-filled and completely filled configurations are very stable configurations. See here, if you write the electronic configuration of nitrogen, nitrogen's electronic configuration is 1s2, 2s2, 2p, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. Nitrogen's electronic configuration is 1s2, 2s2, 2p, 3. And oxygen's electronic configuration is 1s2, 2s2, 2p, 4, 4, 6, 8. See here, if you want to remove this electron, that is the electron present in the p shell, if you want to remove the electron present in the p shell, it is very difficult. That is, more amount of ionization energy is required to remove this electron which is present in the p orbital. Why? Because, see here, if you observe the electronic configuration, p is having 3 electrons in its valence shell. If you fill the electrons in its orbital, see here, 3 electrons are present in the orbitals, p orbital. Therefore, if you remove this electron present in the valence shell, it's very difficult because it is having half-filled configuration. The maximum capacity of p orbital is 6 and half-filled is 3. Therefore, here very much, that is huge amount of energy is required to remove this electron, that is the electron present in the valence shell. Similarly, see here, if you want to remove the electron which is present in the p orbital, then you can easily remove this 4th electron. Why? Because if you remove this electron, that is 4th electron, then it will easily get half-filled configuration. Half-filled configuration. Therefore, very low amount of energy is required to remove this 4th electron because it will get the half-filled configuration. Other example is, if you take sodium, and neon. Sodium is having atomic number 11, neon is having atomic number 10. If you write the electronic configuration, 1s2, 2s2, 2p6, 3s1. Here 1s2, 2s2, 2p6. See here, same reason. If you here the energy, ionization energy is very low because here the very little amount of energy is required to remove this outermost electron, that is the electron which is present in the s orbital. If you remove this outermost electron, it will get a stable noble gas configuration. It will get a stable noble gas configuration. Therefore, very low amount of energy is required to remove this outermost electron, that is the electron present in the s orbital. Similarly, see here the configuration of neon. Here, very huge amount of energy is required to remove this electron, that is the electron present in the p orbital, because it will get, here it is having the completely filled configuration. If you fill the electrons, you will get 1, 2, 3, 4, 5, 6. Here, it don't want to lose the electron because it will get what? Completely filled configuration. This is the reason the ionization energy is more for neon and ionization energy is less for sodium. Because, very important reason, if the elements are having half-filled configuration or completely filled configuration, then they don't want to lose the electron, then very huge amount of energy is required to remove the electron which are present in the half-filled configuration as well as completely filled configuration. This is about ionization energy. Ionization energy means the energy required to remove the electron present in the valence shell, that is the outermost electron. From left to right in the periodic table, the ionization energy increases because the atomic radius decreases. And top to bottom in the periodic table, that is down the group, atomic radii increases, therefore ionization energy what? From top to bottom in the periodic table, the atomic radii increases. Atomic radii increases from top to bottom in the periodic table, therefore the ionization energy decreases. Atomic radii and ionization energy are inversely proportional. Atomic radii and ionization energy. Atomic radii is inversely proportional to ionization energy. Top to bottom, ionization energy decreases because atomic radii increases. Across the period, atomic radii decreases, ionization energy increases. This is about atomic radii. That is the second periodic trend.